Hi, this is Math331, problem solving, lecture 32. We are in the home stretch, and we're going to start off with some computer analysis of the egg drop problem and its generalizations.
Yes, a few of them. So for the egg problem, I wrote a computer program to solve, or to kind of maybe approximate some of the answers. So I'll show you what I did. So if we start out with kind of saying E of n. So I guess firstly, one thing that I did that was different from Professor Miller was I did expected value instead of worst case value. Or worst, like the strategies I was looking for and the answers I was looking for were the expected number of drops, not the lowest worst case or something.
So I forgot, I couldn't put these out until you guys finished the SES scores. Now that you've done that, I can have it out as well.
So right now I will be doing expected value. So yeah, let's say E of n equals, or we could do a little subscript k, where k is the number of eggs and n is the number of stories. I'll make it big. The expected drops with n levels and k eggs with best strategy. And the best strategy would obviously have the lowest expected value. And then
Are you doing analysis of worst case scenario, right?
I was doing expected.
Are you doing, I'm sorry, you're doing expected?
Average scenario. So then I also, for this, defined a second function, which was drop, which would be the level of the first drop. First drop with the best, for the best strategy. And then if we think, then we can see that we can recursively define, the expected value in terms of itself. So that was kind of how I approached the problem. So we can say that, EV of k of n, we're going to drop the first egg at drop, right? So we're going to have, so first we can just say it's that. But then after we've dropped the first egg, what can we say? Well, we're going to have a 1, because we just dropped an egg. And then we're going to have the expected value if it breaks underneath, and then plus the expected value if it breaks above, with their respective weights. So the expected value if it breaks underneath, I got was drop divided by n, with the probability that it would break below drop, times
Is that break at or below drop?
Yeah, at or below drop. Times EV OK minus 1 drop plus n minus drop divided by n times EB of k of n minus drop. And that's, if it breaks above drop, we have the same number of eggs, and now we just check with their same strategy, or, the best strategy, and that gives us the expected value for what's above, and that's below. So that makes sense. And then we can say that, what's EV1 of n? Well,
let's have a little bit larger.
Okay, my bad. EV1 of n is going to equal, the expected value if it breaks at 1 plus the chance it breaks at 1. So that's going to be 1 over n plus, the expected value if it breaks at 2, or the chance it breaks at 2 plus the number of drops. So that's 1 over n times 2, plus, 1 over n times 3, up until, 1 over n times n minus 1. And then you might think 1 over n times n, but it's not 1 over n times n times n. It's going to be another, 1 over n times n minus 1. So if it breaks at the second to top level, you have to check n minus 1 steps before you get there. But if it doesn't break at the second to top level, it's going to have to break at the top level. And this is with the variation of the problem where we know it breaks. And if we're thinking, well, what if we don't know it breaks? That's an equivalent problem to saying you know it breaks and adding a floor, right? If you don't know it breaks, that means it could break above, which you could just say was, the n plus 1th floor, and assign everything above to that. So then, with this explicit formula for EV1 of n, we can kind of define EV2 of n recursively. So EV2 of n becomes a bit more complicated, but so it's going to equal drop 1 first plus drop over n plus or times n minus, or I'll do n plus 1 over 2 minus 1 over n. It's what that turns out to be. Plus n minus drop over n times EV2 of n minus drop. Right? So now, if you know what drop is, which we don't, but if you did know, you could set up a recursive algorithm. And kind of, my idea of what I did for the recursive algorithm was basically, I stored every single value of EV2 of n in, in an expanding list. And then, so then what I would do is, once I figured out how to calculate drop, which I'll talk about next, I would, I'd solve, EV of, 999 and everything below, and then for 1,000, I'd find out drop of 1,000, and I'd calculate this part, which is explicit, and then I'd calculate this, and then I'd just have to check my list. And it made calculating the values, quite fast, actually. So I was able to calculate, into the tens of millions for values. And then there was, so that wasn't the slow part. The slow part was drop. So in class, when we were talking about this earlier, Professor Miller kind of talked about, what would you expect drop to be, right? And we kind of figured out it's probably on the order of square root of n, right? And that was, I think there was some sort of comparison where, it was like n to the 1 minus, whatever the letter was.
Delta.
Sure. And then, plus, and then you can say, if this is anything other than 1/2, this is going to be order greater than n to the 1/2. And, if we're dealing with really big numbers, that's what matters. So, so I hypothesized that drop was going to be of the order, drop would take the form, c root n, or cn to the 1/2. And that c would be some fixed constant no matter what n was. And then the way that I was going to test this was, for every single value of n, I'd take, maybe not every value of drop, but the reasonable values of drop. So from c going from like 1 to 2, for instance. And, I tested smaller cases to see what was kind of reasonable for around where you're going to drop. And so I went through, and for each value of n, I checked a bunch of different drop points. And then once I figured out which drop point was the best, which was quite easy because, this wasn't, we didn't need drop. So in the function, I kind of defined the function, EV, and it took in, n, and it took in c, right? But when we pass, and then, it called itself. But when we call itself, it doesn't matter what c is, because the base case of this function was just checking our list, and if it's already on our list, we're good. So I started out with a few base cases, and therefore every single time I could check, and assuming that I'd gotten the right answer for what I had before, my list was perfect, and all that I needed to do was get this part right, and I guess that part as well. But this part was already good. So it didn't matter what c I was passing in for there. So then, what do you do, right? So I kind of wrote like a double loop. So I kind of had, for n, 1 to, 100,000, let's say, right? And then I had, for c, within some certain range, which was probably like, once we got, fairly precise, it was like, 1.33, not 5, 1.38 to 1.42. And then I would adjust c, and c was kind of adjusted dynamically depending on how big n was, so that c would take on every single possible value to get every single possible value of drop within, right? So like 1.38 times root n was, the lower bound, and 1.42 times root n was the upper bound, and I tested every number in between. And I found which value of drop, and then, so within this, I passed it into this function for every value of c, and then I took which value of c gave me the best result, and I stored c, and I stored the value, and then I kept on going. So then,
if you run this again, you probably want to go a little higher than 1.42, so root 2 is more symmetric.
Yeah. So what
It shouldn't really make a difference.
what I did was I started out with bigger bounds, and I kind of checked my answers, and then I saw that it was converging. And then, especially when it got bigger, checking all of them was really hard.
Yep.
So I decided that, instead of checking all of them, I would just run it on really big numbers, and get cool answers. And then I put in a slight check, which was, if 1.42 is the answer, tell me, and then I might adjust my bounds upward. But I kind of figured out what the answer was, fairly early on, or what I guessed the answer to be. And then it was just, seeing how big a list I could generate in a reasonable amount of time. And, whatever. But yes, you could make it a bit bigger. But I think I did that for the smaller cases. And then, well, what does this tell us? So the reason why I did this was so that I could look at C, right? And there's two possibilities. C is independent of n. C stays constant throughout, or C is a function of n. And if C is independent of n, then this hypothesis is correct. C stays constant. It's great. We have our formula. We don't know why it works, and we haven't proved it, but we know it's probably true, especially if it comes out with, root 2, which is, not a number that you coincidentally come out with very much. And then if C changes a lot with n, then you might want to revise. You might want to say, maybe this wasn't the best hypothesis. If C looks like C's also, n to some power, then maybe drop is, n to the 2/3 power or something. But that wasn't the case. So mainly this code was to check this hypothesis. And once this hypothesis was correct, I was able to do more things.
So basically what works for worst case is also working for average case?
In this example, yes. So, yeah, I got the results. It converged quite quickly. A few things were, it was not always root 2. So at the beginning it wasn't, because, if n is 1, you check at 1. Or I guess you don't have to check. If n's 2, you can check at 1 or 2. So at the beginning, because of end effects and those sorts of things, it doesn't really. There were some things that distorted it, and also because it was discrete and this looks continuous. And those effects actually stayed with it if you're trying to get very precise for quite a while. Because it's recursive. So, if one method is slightly faster because of, some sort of, if, like expected value of 9, for instance, is slightly faster than, what your continuous model would suggest, or slightly lower, then when you check things that depend where, n minus drop is going to be 9, then they're going to be slightly lower than you'd expect. And that evens out over a long time, but not, super fast. But C converged to root square root of 2. There were some variations in C, but I was able to show that was more error with kind of discrete and rounding stuff than with any actual difference in the square root of 2. And then what I was trying to do this morning, but my computer could not handle the data that I was putting in, was run a regression. So if you look at, well, I guess I'm getting a bit ahead of myself. But when I got to the expected values, I printed them out too, and they looked, like a nice square root of 2, which would make sense, that they'd be on some order of the square root of 2.
Is there an expected value for C?
For n. For n. So first, I guess, right, drop of C of n, right? And then for any value of n, we kind of looked at in class, the worst case, I think, for our first, strategy was kind of like 2 root n, and then we modified it a bit downwards to root 2 root n. If the worst case is root 2 root n, you'd expect the average case to probably be on the same order, but a little smaller than the worst case. And that's what happened. I think the average case was around just square root of n. That's how the numbers happen to be. I have no idea
Which makes sense because the worst case was like, root n plus 1. I'm sorry, we want like m plus 1 over 2 to equal n.
Yeah.
So we would have it as about square root of 2, square root of n for worst case. So the average case should not be larger than the worst case.
Right. Yes. I was thinking it wouldn't be worse. I didn't know why it was exactly 1, which seemed to be the case when I ran the regression, which I'm not sure why. But that was the case. And it looked like it was just square root of n, and, it was very, like the r squared value is like 0.9999999. So that was, satisfying. It was nice that it worked out. And then you can do it with higher values of k. So so the reason why this was easy was because I had an explicit formula for EV of k minus 1. Right? EV of 1 is just you check everything. Once you found the first 1,000 values for EV of 2, you can find the first 1,000 values and maybe a little more than the first 1,000 values of the expected value for 3x, because you can just check your table when you're calculating the expected value. So I did that, and I got some values of c. I got I did when k equals 3 and k equals 4. My computer cannot handle much greater than that. So when k equals 3, c converged to around 1.6, which was a number that I could not make any sense of.
Anybody know any numbers close to 1.6? Yeah, golden mean.
I mean, that is true. Maybe it was that.
This could be a complete coincidence. But I'm thinking like the continued fraction expansion of square root of 2, continued fraction expansion of golden mean.
Okay.
So
Well,
let's see what 4 is.
Yeah. So maybe we could check golden mean. I'm not sure if it ever got precise enough with k equals 3 to check enough digits. And then when k equals 4, this one I was not as sure about because I was only able to check up to 100,000. For the other ones, I was able to check to around 1 million. But I got c was coming out to be around 1.65. And again, I wasn't exactly sure why it was that. That also seemed a bit large. I don't know. I guess for smaller numbers, it wasn't this large, right?
Well, the first thing is, do you expect the constant should be increasing as k increases? And are you doing things to a different power than square root of n?
I was doing things to a bigger power than square root of n.
So for k equals 3, were you doing it to n to the 2/3?
Yes, I did. I didn't screw that part up. Yeah, so this was c, right. So maybe I'll make it clear. So that was drop of 2, and then in the more general case, drop equals, c times n to the, k minus 1 over k.
Yeah. And you should probably say it's c sub k.
C sub k.
And so the problem is, since the exponent of n is changing, ck is going to change, and I don't know that ck has to be growing.
Right. But what I did get was c did converge in all the cases, which was strong evidence that the square root, that it was of the form c to the k minus 1 over k, or cn to the k minus 1 over k, and not some other form, because if it was some other form, c would probably be dependent upon n.
What would be great is if we could show that ck has to be at most 2. Maybe ck is a monotonically increasing sequence, in which case now this could be a new universal constant. The infinite egg drop constant.
Perhaps.
So this is how you get research ideas. You take something like this, and you ask yourself, how can I generalize? What's going on? What's interesting?
Yeah.
If you have this sequence of numbers that's increasing, and how much data do we need?
I think that with the data aspect, I think if you wanted to be slightly less precise, and you weren't concerned about getting every single value completely right, I did the whole thing and actually talked to Professor Miller about it, and then I went home and I realized that one of my base cases was wrong. But it didn't affect, what C was at n equals 1,000,000. It affected what C was, for the first 100 values maybe. But fixing it really had no effect. So I think if you're willing to tolerate those little deviations, you can get up to really big numbers. One thing that was what made it increasingly more difficult was I had C go up by an order of I think it was like C by like 0.5 divided by n to the relevant power, so n to the k minus 1 over k. So that way, you're multiplying it by n to the k minus 1 plus k. That way you don't have any rounding errors or anything, right? You're checking every single value and you're sure, because you have to round, obviously. So that was, that makes it increasingly harder as k gets larger. For 2, that wasn't that hard because square root of 2 isn't that large, or isn't that large. But the 7/8 root of something would be quite large if n was 1,000,000, and checking 1,000,000 different values of C for each value of n, well, took my computer a lot of time. This was not a fun experience for my computer. It crashed several times. So yeah, I think that was mainly all I was going to talk about. I was trying to do some analysis on kind of deriving the stuff, but I didn't get any answers that made sense. So I'll try again.
Excellent, thank you. So we'll switch the electronics. So this shows a lot of really good items here. So for Friday's class, I'll talk about some other problems where you use expectation. We do the geometric series formula in this class by shooting basketballs. I've got 5 minutes. All right, chalk me. I gotta go fast. All right, geometric series formula in less than 5 minutes using expectation, very similar to what we just did over here. So imagine 2 people are playing basketball. We'll say Bill Murray and Michael Jordan, or one of the aliens from Space Jams. And we will assume that when you shoot, you always have the same probability. So our first player always gets a basket with probability P. Our second player always gets a basket with probability Q. So this is for make, and then miss will be 1 minus Q, 1 minus P. So they both miss with probability R, which is 1 minus P, 1 minus Q. First one to get a basket wins. So let's let X equal the probability first shooter wins. Okay? So we want to calculate X. So what's the probability the first shooter wins? Well, how could the first shooter win? They could win on their first shot, they could win on their second shot, they could win on their third shot, and so on. So to win on their first shot, it's simple, it's P. To win on their second shot, both people must miss, which is R, and then they must hit. To win on their third shot, both people miss twice, and then... So we see this is a geometric series. I've got to do this fast. And we get P 1 plus R squared plus dot dot dot. And so we can calculate this probability if we know the geometric series. We can now go backwards and use this to get the geometric series formula.
And clearly R is going to be between 0 and 1. The only way R could be 1 is if both people have no chance of making a basket. We're not going to watch this movie. You know, there's no way Warner Brothers would ever make that film. Let's calculate it another way. Imagine we want to calculate the probability the first person wins. Well, they could make their first basket. And now imagine they both miss. From this point on, what is the probability the first person makes the first basket? Not P. That's the probability they make the next. That's the probability they make the basket they're shooting right now. It would just be X. It's a memoryless process. So this is one of the key ideas. So this implies that X, we bring it over and get 1 minus R times X equals P is P 1 over 1 minus R. There you go. There's the geometric series formula from shooting hoops. Now what's interesting is, in the geometric series formula, what do you want to normally assume about R? So I could take R equals negative 15, and that would work. Okay? The absolute value of R is less than 1. This only works if R is between 0, less than or equal to R less than 1. So unfortunately, if we have a negative value of R, this argument doesn't make sense because there's a physical game going on. And you are not going to have a negative probability of making a basket. Or you're not going to have people having a greater than 100% chance of making baskets. How could we extend this argument to negative values of R?
Shouldn't it just be greater than 0? It's not greater than 0.
Sure, but what I will say is that I can actually handle the case I equals 0. So one thing is we could use complex analysis and say, look, I have this formula equals this formula. It turns out this formula will still make sense for negative values of R and try to do some kind of analytic continuation. That's a bit hard. What you could do is if you have R as negative, split it up into the odd and the even terms. And then what you can do is you could have 1 plus R squared plus R cubed plus dot dot dot. This is equal to 1 plus R squared plus R to the 4th plus R times 1 plus R squared plus R to the 4th. Now for each one of these, I know what's going on because it's a positive ratio. And I get 1 over 1 minus R squared plus R, am I doing this correctly? 1 over 1 minus R squared. I now get 1 minus R over, did I make a mistake? No, 1 plus R over 1 minus R squared. When you factor the denominator, there you go. 1 over 1 minus R. Okay? All right, we did it hopefully in less than 5 minutes. Unfortunately, if I went over, you can check because the video has timestamps. All right.